Hello everyone, welcome back you all in this new video where we are going to see the professional approach for the manual design of two-way slab. This complete problem we are going to solve in 5 important steps. In the first step we will see the problem statement in details along with the type of the slab, trial depth, effective span as per the codal recommendations. In the second step we will go for the load calculation, maximum moments, depth check for the flexure. In the third step we will go for the design for the flexure for finding out the reinforcement in both the spans, and also we'll go for the designing of the shear. In the step 4 and 5 we will go for the deflection check and we will prepare the final schedule and detail as per the design results. And in the last I will discuss about some bonus tips and tools for designing of the two-way slab in less than of 2 minutes. So don't miss the end of this session. Now without wasting time, let's start to discuss about the problem statement. So here we have to design a floor slab as S2 which is present here, which is having the clear dimension as 4 meter by 5.5 meter. This is the floor plan of a residential building. This slab is supported by from all of its sides as a beam of width 230 mm. We have to assume the live load as 3 kN per meter square and the floor finish load as 1 kN per meter square. The material we have to use for the designing of this particular slab as M20 as a grade of concrete and Fe415 as a grade of steel. So very first we have to write all the available data and given data. So supported beam width as 230 mm. The material we have to use as M20 and Fe415 as given in the problem statement. The loading over the slab as 3 kN per meter square as a live load and floor finish load as 1 kN per meter square. We are going to assume that the clear cover for this slab as 20 mm and the diameter of bar as 10 mm. This is what the assumption. On later stage it may get changed. The clear dimension of this slab as 4 meter and 5.5 meter as given in this framing plan. The width of this floor slab is 4 meter and length of this slab is 5.5 meter. Always the shorter span you have to consider as width, longer span you have to consider as length. With all of this given data we are going to start the design, and before of starting we first have to decide whether it is a one-way slab or two-way slab. So for that reason we have to take the ratio of shorter span divided by longer span. As we earlier discussed that always the smaller span you have to consider as length as along the direction as x, length along the direction y you have to consider as longer span. Shorter span divided by longer span, this ratio we are getting as 1.3546. So which is what less than of 2. But we know that if this ratio is less than of 2 then it will become two-way slab. But if ratio you are getting as more than 2, at that time it is going to become one-way slab. So from this step we are concluding that the proposed slab is actually two-way slab, and according to this two-way slab we have to execute the later steps. Now next we have to find out the trial depth, how much the depth of the slab is required. So for that reason we have to look at IS 456-2000 clause number 23.2.1 page number 37. So this clause will tell you how you can decide the depth of the slab, and that will be what your trial depth. In IS 456 page number 37 clause number 23.2.1, this is going to define span to effective depth ratio for the different types of the slab. So if you are going to deal with the cantilever slab, so the ratio will be what? 7. If you are going to design the simply supported slab, then you have to consider 20. Then if you are going to design as a continuous slab, then you have to consider it as 26. So it is what? Span to effective depth ratio will equal to this as 26. So why here we are going to consider 26? Because it is a continuous floor slab. In our problem statement it is a floor slab, so it is having the continuity from different sides. On this side it is having discontinuity, on this side it is having discontinuity, but on this side the slab is present, on this side is slab is present. So it is one kind of continuous slab. So that's why we are going to consider the case of span to effective depth ratio for the continuous type of the slab as 26. But here one more thing is there, that is modification factor. In general it will be what? Your span to effective depth ratio will equal to 26. But when you are going to find out the value of effective depth, so the formula is going to become effective depth will equal to span divided by 26. Now here we have to multiply it with the modification factor. What it means by modification factor? Modification factor is going to consider the presence of percentage of reinforcement in your element, because if you are going to consider only length divided by 26, it means that there is a consideration of role of your presence of concrete only. But in actual, we know very well that in concrete slab there is the presence of reinforcement also. So reinforcement will also taking a part of resisting the load. And if you are going to consider the presence of percentage of reinforcement, so demand of the depth will decrease definitely. So that's why we have to consider the impact or presence of reinforcement in your concrete slab. So that's why we have to consider here as modification factor. And in the statement here it is given depending on the area and the stress of steel for the tension reinforcement, the main reinforcement, the value in clause A, here all the recommendation were made in A, that should be what modify by the multiplying with the modification factor. So we have to calculate this modification factor. But to calculate actually the modification factor for your proposed example, you need to have the presence of percentage of reinforcement. But you know very well, till now we have not done the design for the reinforcement. That's why what we need to wait for calculation of the reinforcement. But at initial stage we have to assume this value. For that reason, it is the recommendation that the assumed value of modification factor should be 1 to 1.5. In between of this range, you can assume the value of modification factor. So here I am going to consider the modification factor as 1.5. With this modification factor, what is the span? Span to effective depth ratio. You always have to consider the shorter span. So basic formula is what? Your span to effective depth ratio is equal to 26. Now I am going to modify it to calculate the effective depth. So effective depth will equal to shorter span divided by 26. New term is going to be introduced here as modification factor. So what is the role of this modification factor? It is actually the consideration of percentage of reinforcement present in your concrete slab. But right now we don't have the design for the reinforcement. That's why we are going to assume this value as 1.5. Now shorter span is how much? Clear shorter span 4000. We are having two span. One is your width 4 meter and this 5.5 meter. So always you have to consider the shorter span. Remember. So that's why I am going to consider here as shorter span as 4000 divided by 26 multiplied by 1.5. After doing this calculation, we are getting the value of 102.564 mm. So this much effective depth required based on the serviceability criteria as per this codal recommendation. Now here this is the effective depth. Now we are going to assume as clear cover as 20 mm and diameter of bar as 10 mm. So it is actually suppose your slab and we have calculated the effective depth. This is what your suppose effective depth. Now effective depth means it is the center of your reinforcement. Now half of this diameter of bar plus clear depth. This all addition will give you overall depth of your concrete slab. I am going to add all these three terms, effective depth plus clear cover plus half of your diameter of bar. So I am getting overall depth requirement as 127.564 mm. This much the overall depth is required based on the serviceability criteria. Now I am going to provide or I am going to assume based on this recommendation overall depth as 130 mm. Now we have to do the reverse calculation to find out finally available effective depth. So how much the effective depth available? That will equal to finally provided 130 minus clear cover that we have assumed minus half of diameter of bar. Reverse calculation, we are getting the effective depth as finally available as 105 mm. This much effective depth is what required and available. With this effective depth we are going to do the further calculation and later on we will decide whether this available effective depth is safe or not. So it is actually the trial depth. It is actually what? Trial overall depth of your slab. Now next, for further calculation we need to have the effective span along both of the direction. So as per the codal recommendation, effective span will equal to clear span plus width of the supporting beam. In actual what it is? Clear span, suppose this is your slab, floor slab, and this is going to be supported by beam from this side, it is going to be supported by beam from this side. Okay, now it is the clear span having as 4 meter. Now this clear span plus half of the support from this side, half of the support from this side means center of this support. So this is basically giving your effective span of the slab in both of the direction. So 4 plus means 230 width of the beam is there. So 230 half from this side, beam width half from this side, beam width half from this side. So this half and half is going to become 1 simply. So clear span plus 0.23 will giving you 4.23. Next, along the longer span, it is the shorter span and it should be what? Your longer span. Longer span. So it is going to become 5.5 plus 0.23. Totally is going to become 5.73 meter. So shorter span 4.23, longer span 5.73. Thereafter, in next step, we have to do the load calculation. How to do the load calculation? Now, very first, self weight of the slab. How much the self weight slab will be? So we have to calculate the loads in terms of kilonewton per meter square area. Suppose this is the floor, per 1 meter square area, how much the load is there. So how you can do this calculation? This is the density of the material. We are going to build it with the concrete. So concrete is having the density as 25 kilonewton per meter cube. And we have to calculate the loading in kilonewton per meter square. So how you can do this? So 25 multiplied by overall depth of slab. So it is in kilonewton per meter cube. Focus on the unit. Multiplied by in meter if I am going to put the depth. So meter and meter get cancelled. So the remaining term will be what? Kilonewton per meter square. So that I am going to put here 25 multiplied by 0.13 is your overall depth. If you are going to multiply both of the things, you are getting the self weight of the slab as 3.25 kilonewton per meter square. Floor finish load is given as 1 kilonewton per meter square. Lie load on the slab is given as what? 3 kilonewton per meter square. Total load that is going to be subjected to your slab will become 3.25 plus 1 plus 3. So this summation will give you service load. But for the designing, we need to have the ultimate load, or we can say the factored load. So for this reason, we have to multiply this addition, service addition, with a 1.5 factor. This is the factor for the loading for the ultimate design, for the factored loading. So here we are getting factor addition as 10.875 kilonewton per meter square. So this is what the load calculation. Now in next step, we have to do the calculation for the maximum moment and depth for the flexure. So for the case of the two-way slab, we need to understand some important things. For that, you need to look at this figure. So here it is given as the two-way slab. So two-way slab is going to be subjected to the movement in both of the direction, along the shorter span as well as along the longer span. So both of the spans is going to be subjected to deflection and going to be subjected to effective movements. So whatever the movement is going to be developed, against that movement, we have to provide the reinforcement. If you are going to talk about the one-way slab, so for the case of the one-way slab, only the shorter dimension will be what? Effective. Your slab is going to be deflect along the shorter direction only. Along the longer direction, it is not going to be subject to deflection. That's why for the case of the one-way slab, it is needed to provide the reinforcement along the shorter direction only. But for the case of the two-way slab, your slab is going to be subjected to deflection in both of the direction. That's why we need to calculate the movement. As in this figure also you can understand, here I have provided the reinforcement as the main reinforcement in both of the direction. This is what the difference between the one-way slab and two-way slab. So our proposed floor slab is actually the two-way type of the slab. That's why we have to calculate the movement in both of the direction. Now for calculating the movement, first we need to calculate the movement coefficient as recommended by the IS 456. If you are going to see IS 456 2000, page number 91, table number 26. So in this, there are different types of the panels are present based on the continuity of the slab. As in our proposed example, this is the continuous type of the slab. It is having the discontinuity from this side, it is having the discontinuity from this side. But this floor slab is actually continuous from this side, continuous from this side. So actually you have to decide the type of panel. Which type of panel it is? It is the interior type of panel, means having the continuity from all of its sides. It is the what? Only discontinuity from one side. It is having the discontinuity from two sides. It is having the discontinuity from all of its sides. So based on all these criteria, IS 456 has defined 9 types of panels. Amongst all these 9 type of panels, our proposed floor slab falls under the category of under the type of panel as 4. 2 adjacent edges are discontinuous. If you are going to see our example, so here it is discontinuous, here it is discontinuous. So 2 adjacent edges are actually discontinuous. So this is our proposed type of panel. Now based on aspect ratio, how much the aspect ratio is? So after doing the calculation, look at this aspect ratio. Effective span along the longer span, effective span along the shorter span. If you are going to do this calculation, so we are getting the aspect ratio as 1.354. So that I am going to consider here 1.354. So it is falls in between 1.3 and 1.4. So that's why here two adjacent edges are discontinuous and aspect ratio falls in between these two. So we have to do the linear interpolation and we have to calculate the moment coefficient for the negative moment at the continuous edge and positive moment at the mid of the span, as our proposed slab is actually what continuous type of the slab. So in case of the continuous type of the slab, over the support there will be the negative moment. As you can see, the red color actually showing the negative moment because it is a continuous support. So it is going to experience the negative moment over the support. Here the negative moment, but at the mid of the span there will be the positive moment. So accordingly we have to calculate the moment coefficient, negative moment coefficient as well as positive moment coefficient for the shorter span. And for the longer span also there will be the negative moment of the support, negative moment at the support alpha y as negative and positive moment coefficient at the mid of the span of the longer span. So this thing is actually defined by your code also. Here the negative moment at the continuous edge, continuous support, positive moment at the mid of the span. So for 1.3 what value is there, for 1.4 what value is there, and our aspect ratio is in between of this 1.3 and 1.4. So you have to do the linear interpolation, and after doing the linear interpolation we are getting the values as negative moment coefficient alpha x as 0.068276 and negative alpha y as 0.047, right? Positive moment coefficient at the mid of the span as alpha x 0.0512, alpha y positive 0.035. Now amongst these alpha x and alpha x both are negative and positive. So amongst these two values we have to consider the maximum one. So here the maximum coefficient is actually what, 0.068276, that I am going to consider final alpha x. Now amongst these two value I am going to consider the maximum one, so I am getting the maximum as 0.047. Now in respect of these two moment coefficient we are going to do the calculation in both of the direction. So alpha x multiplied by ultimate load multiplied by shorter span. For y direction also you have to consider the shorter span, where it is given in your code only. This is what defined. In both of the direction you have to what, only change the moment coefficient. Rest of these two parameters will be same, ultimate load multiplied by shorter span square. So in respect of this formula I am going to do the calculation. Alpha x for the shorter span, then factored load as 10.875 multiplied by shorter effective span as 4.23. After doing calculation we are getting the factored moment along the shorter span as 13.2855 kilonewton meter, along the longer span 9.1455 kilonewton meter. Now amongst these two we have to consider the maximum one to calculate the how much the effective depth required for the flexure. Means what, whatever the maximum moment is going to be developed, to resist that maximum moment how much the effective depth is required. That is what the concept. Now the formula to calculate the effective depth required for the flexure is changing in respect of your grade of steel. So for Fe415 grade of steel, the limiting moment will equal to 0.138 FCK D square. If you are using the higher grade of steel as Fe500, so the formula is changing to 0.133 FCK BD square. But in our proposed example, we are using the grade of steel as Fe415. That's why formula is going to become maximum moment will equal to 0.138 FCK BD square. So our maximum moment is what, 13.2855. So if you are going to modify this formula, so the value is going to become D required will equal to square root of ultimate moment divided by 0.138 FCK B. B is your width of the slab considered in the calculation. So we are going to consider the width of the slab as 1000 mm, that is 1 meter, and characteristic strength of your concrete slab is 20 and 0.138. Ultimate moment is what, 13.2855 into 10 raised to 6. After doing the calculation we are getting the effective depth required for flexure to resist this much higher moment is 69.38 mm, and available effective depth is what, 105 mm is your overall available effective depth, and requirement is how much, 69.38 for flexure only. So provided or available depth is more than of your required one, hence provided depth is safe. In some situation, in some calculation, you are getting the value of depth required as more than of your available depth. In that situation, you have to revise the design and you have to make the available depth more than of your required depth. Next, we have to find out the how much reinforcement required in both of the direction. We have done the calculation for the movement. So in both of the direction, we got the movement. Now in respect of these movements, we have to find out how much the reinforcement required along shorter direction, how much the reinforcement required along the longer direction. So I am going to do this calculation. So here reinforcement along the shorter span. The formula for calculating the reinforcement is 0.5 multiplied by characteristic strength divided by yield strength. Inside bracket 1 minus under root of 1 minus 4.6 ultimate strength in the considered direction divided by characteristic strength width of the slab considered multiplied by effective depth available. Then overall multiplied by considered span width of the slab multiplied by effective depth available. Just put all these values in this formula. 0.5 multiplied by characteristic strength as 20, yield strength of the steel as Fe415, that's why we are considering as 415, and here ultimate movement is actually along the shorter span. How much the value is? 13.2855. So that I am going to put here as 13.2855 into 10 raised to 6 divided by all this value FCK B effective depth available as 105 square multiplied by B 1000 multiplied by effective depth as 105. After doing this calculation, we are getting the value of 379 mm square. This much area of reinforcement required along this shorter span. We have to provide this much area of reinforcement. Now this is the design requirement, but IS code is recommending that for the slab in each direction minimum percentage of reinforcement should be what? 0.12% of sectional size, means B and overall depth. 0.12% B 1000 over 1 meter width of the slab. We are going to make the calculation multiplied by overall depth, and 0.12% it is, so divide by 100. Okay, so after doing this calculation, minimum area of reinforcement should be in both of the direction as 156 mm square. So demand along the shorter span is what? 379, and minimum requirement is what? 156. So among these two values, we have to consider the maximum one. So design requirement is more than of the minimum requirement, means we have to follow the design requirement. In some situations, suppose you are getting what? Design requirement as 150 only, and minimum requirement you are getting 156. So which one you have to follow? At that time you have to follow the minimum one. Now next, following the required reinforcement as it is more than of the minimum 379. Now I am going to provide 8 mm diameter of bar. So unit area of 8 mm diameter of bar is going to become 50.26. That you can calculate from pi by 4 d square. Put the diameter here, so you will get unit area of 8 mm diameter of bar as 50.26. Now how much the spacing is required? So unit area divided by total area required 379 multiplied by or a considered width of the slab. So 1 meter width of the slab we are considering. So after doing this calculation, we are getting the spacing required as 132.61 mm. So we have to provide the reinforcement along the shorter span with a spacing of 132.61. So for the safety concern, I am going to provide the spacing as 100 mm only. I am going to make the bars as close as than that of the requirement. So that's why little bit more percentage of reinforcement I am going to provide. So spacing I am going to reduce to 100 mm. So 8 mm diameter of bar at a spacing of 100 mm center to center along the shorter span. Now finally I had to calculate how much the area of reinforcement I am going to provide, because as per the calculation 132 mm is spacing, but what I have done, I have reducing the spacing. So obviously number of bars and area of reinforcement is going to increase. So that's why I need to do the recalculation. So unit area divided by finally provided spacing multiplied by considered width. 1 meter width we are making in consideration. So overall finally area of reinforcement is going to be provided as 502.6 mm area of reinforcement we are going to provide. Requirement was 379 to resist the movement. We are going to provide 502. So little bit more than that of the required we are going to provide. How much the percentage of reinforcement is provided? So total area provided divided by section size. So B into overall depth. Okay. So B is 1000 considered width. Overall depth is 130 mm. So we are providing the percentage of reinforcement along the shorter span as 0.386. Percentage of reinforcement we are providing which is more than of 0.12%. Hence it is okay. Now same calculation you have to do for the longer span also. So here here we have to just change the ultimate moment. So here ultimate moment along the longer span is 9.1455. So I am going to put here the same value, and after doing the calculation we are getting the area of reinforcement required as 254.12. Again I have to compare it with the minimum requirement. So after comparing with the minimum requirement we are getting the more value for the design requirement. Okay, so we are going to follow this one again. I am going to provide 8 mm diameter of bar. Unit area is going to become 50.26. So unit area divided by total area required multiplied by 1000 per meter width of the slab. 197.78 mm spacing is required. So you have to reduce it to 175. Okay, so here providing 8 mm diameter of bar at a spacing of 175 mm means 197. Lower value will be what? You can take 190 also. You can take 180 also. Why I am taking 175? Because we are going to round down this value by 25 mm. So lower value is going to become what? 175. Now 8 mm diameter of bar at a spacing of 175 mm. Now finally how much area of reinforcement provided along the longer span? So that is going to become what? 50.26 divided by finally spacing multiplied by over the considered width. So we are getting total area as 287.2 mm area of reinforcement provided. Requirement was what? 254 only. How much the percentage of reinforcement provided along the longer span? So total area of the reinforcement divided by sectional area 1000 multiplied by overall depth as 130. So we are getting the percentage of reinforcement as 0.2209 percentage. This is again more than of 0.12%. In both of the direction you have to provide the percentage of reinforcement more than of the recommended by the IS code. IS code said that minimum percentage of reinforcement should be 0.12. So it should be either equal to or more than of the 0.12%. So it is again passing the codal criteria, codal recommendation. So in both of the direction we have provided the percentage of reinforcement more than of the minimum recommendation. Next we have to go for check and design for the shear. It means that first we are going to check whether it is needed to design for shear or not, and after that we are going to design for shear. So first we need to calculate the ultimate shear force. So the factored maximum shear force per unit width of the slab, that is VU, may be obtained by considering that maximum shear force will be developed at a distance of d from the face of the support. So suppose this is the shorter span of your slab and this is the supporting beam. So from the face of the supporting beam we are going to consider the section for the maximum shear is at a distance of d from the face of the support. So WU ultimate factored load, that is 10.87 multiplied by shorter span divided by 2, the total span, clear span divided by 2 half we will get minus the effective depth. Effective depth available is what? 105. In meter it is going to become 0.105. So after taking all this value here, ultimate load multiplied by clear span divided by 2 minus effective depth, so we are getting the value of ultimate shear force as 20.608 kilonewton. This much the shear force. Now we have to calculate how much the nominal shear stress is going to be developed at this section. So that will be equal to ultimate shear force divided by width considered multiplied by effective depth of the slab available. So 20.608 into 10 raised to 3 to make in Newton divided by width 1000 mm we are considering, effective depth as 105. After doing this calculation we are getting the value of 0.196 MPa stress at this particular section. Next we have to calculate how much the capacity of this section. Actually what? This much shear stress is developing at this particular section. But what is the critical capacity? Up to what value this section can carry the stresses? This is what? Due to loading and available section, how much the capacity for resisting the shear, that we need to calculate due to presence of the percentage of reinforcement. So as per the IS 456-2000 table number 19, in respect of the percentage of reinforcement and grade of concrete, we have to calculate the critical shear resisting capacity of this section. So tau c we have to calculate. So go to look at table number 19 of IS 456-2000. So here in IS 456 table number 19, So this is what defining the critical capacity. So here we need to know the percentage of reinforcement. So how much the percentage of reinforcement provided along the shorter span? So we have provided the percentage of reinforcement along the shorter span as 0.386 percentage. So this falls in between the range of 0.25 and 0.5 because the value is not exactly available for this 0.38. So that's why our value is falling in between of this range 0.25 to 0.5, and our grade of concrete is M20. So for M20, for 0.25 it is 0.36, for 0.5% it is 0.48. So we have to do the linear interpolation. I am going to put the values here. So we have to calculate the value for this 0.386. After doing the linear interpolation, we are getting the critical shear resisting capacity of this particular section as 0.4253 Newton per mm square or MPa. So nominal shear that is going to be developed at this particular section due to loading is actually 0.196, which is less than of the critical capacity. Means permissible capacity is what? 0.4253. So actual stress is less than of the capacity. It means that hence provided slab is safe in shear, and hence no need to design and provide the shear reinforcement. So basically our check is passing, hence we don't need to provide the shear reinforcement as well as we don't need to design for the shear. Now next, finally we have to check for the deflection. Our provided depth is safe in deflection or not. Okay, so as per IS 456-2000 clause number 23.2.1 as see page number 38, we have to do the calculation for the modification factor. At the start of this calculation, we have assumed the modification factor. Have a look over this. We have considered the modification factor as what? 1.5. Now this modification factor actually we are going to calculate, because for calculate the modification factor we need to have the percentage of reinforcement. So initially we don't have the percentage of reinforcement, that's why we are assuming the value. Now we are having the percentage of reinforcement, that's why we can calculate the effective length factor actually. So provided percentage of reinforcement along the shorter span is what? 0.386. Now stress in steel, look at your IS 456. So on this page number 38, modification factor for the tension reinforcement, for the main reinforcement. Okay, so modification factor we had to calculate. So first we need to calculate the FS, stress in your reinforcement. So the formula for the stress is actually given here. 0.58 multiplied by yield strength of your steel multiplied by area of reinforcement required divided by area of reinforcement finally provided for the considered direction. So here in the calculation we are considering the design span as shorter span. So along the shorter span percentage of reinforcement is 0.38. Now stress in steel, that is 0.58 multiplied by yield strength. So Fe 415 we are using, so 415 is going to become your yield strength. Area of steel required. So while doing the calculation along the shorter span, initially area of reinforcement was required as 379 and we have finally provided as 502.6. So these two values we have to put in this deflection check criteria. Okay, so area of steel required 379 and area of steel provided 502.6. After doing this calculation, we are getting the FS stress in steel as 181.507 MPa Newton per mm square. Now KT is actually your modification factor. Okay, 1 divided by this formula is there where FS value you need to have and percentage of steel you need to have. So FS value we have calculated in this equation. Now put the values. 1 divided by 0.225 plus 0.00322 multiplied by FS 181.507 minus 0.625 log to the base 10, 1 divided by provided percentage of reinforcement along the considered direction. After doing all of this calculation, we are getting the value of modification factor as 1.81. Therefore, span to effective depth ratio actually we are getting as effective span I am going to consider 4230 divided by effective depth available. Actually here it should be what? Effective depth. So it should be 105. I need to correct it, 105. So after doing this calculation, what value I am getting? So it is actually 4230 divided by 105. So it is going to become 40.28. Now permissible span to effective depth ratio is how much? So span to effective depth ratio for the continuous slab is what? 26. Now 26 I am going to multiply with the calculated modification factor. So if you are going to multiply this value, we are getting the span to effective depth ratio permissible value as 47. So actual ratio is 40.28 and permissible ratio is 47.18. So your actual value is less than of your permissible value. Hence, slab is satisfying the deflection criteria. Your design is safe in the deflection criteria as well as your provided depth is safe in the deflection criteria. Now next, finally, in respect of this design result, we are going to prepare the schedule and detail. So here the slab is what? S2, overall depth is 130, reinforcement along the shorter span 8 mm dia at a spacing of 100 mm center to center, and along the longer span 8 mm dia at a spacing of 175 mm center to center. This slab is actually the type of two-way slab. The detailing will be like this. Here along the shorter span, that is 4 meter, the reinforcement will be 10 mm dia at a 8 mm dia at a spacing of 100 mm center to center, 8 mm at a spacing of 100 mm center to center, and along the longer span 8 mm dia at a spacing of 175 mm center to center. Okay, this is what the section along the shorter span 8 mm dia at 100 mm center to center. Distribution reinforcement means reinforcement along the longer span 8 mm dia at a spacing of 175 mm center to center. This is a section along the longer span. So hope that you all understood the complete problem along with its scheduling and detailing. Now the same problem we are going to design by using this advanced Excel sheet. This advanced Excel sheet is capable of designing all types of different slabs. So first of all, as per the given data, we are going to edit the values only in yellow cells. In the white cells, you don't need to try to change anything. And in this cell, this will suggest this suitable value. The black cell you have to skip. And in the red cell, you will get the danger or the sign of the failure. So here the grade of concrete is what? M20, and grade of steel is Fe415. What is the shorter span? Is 4 meter. Longer span is 5.5 meter as per our problem statement. And now here we have to decide the type of the panel. So is it what decided by this Excel sheet itself as it is one-way slab or two-way slab? Like suppose you are going to put the span as 20 meter longer span. So it is going to become one-way slab. But if you are going to put the value as 5, so it is going to become two-way slab. Now it is two-way slab, we have to decide the type of the panel. So two adjacent edges are discontinuous, that I am going to choose. So all the type of panels are actually present here, right? Now next, I am going to assume the overall depth. Here you have to make the assumption to match with our calculation. I am going to assume the overall depth as 130 mm. So that I am going to here assume as 130 mm. Later on we are going to perform the check whether this project depth is safe or not. Now supporting beam width is 230, clear cover as 20, side cover as 30, minimum diameter of bar I am going to consider as 10 mm. Okay, it is what assumption. It is the values only in yellow cells. Now the sheet is going to calculate the effective depth and effective spans, everything where the sheet is going to be done on itself. Now next, sheet is also going to calculate the movement coefficients. You don't need to look at the IS code. Now here the self weight of the slab is going to be calculated by the sheet itself, as here 3.25 sheet is also doing the same calculation. Floor finish, here the floor finish you have to adjust through this density of the flooring material plus the thickness of the flooring material. So these two variables is deciding the how much the floor finish will be. So I am going to take here as 50 only. So floor finish is going to become 1 as in our problem statement as 1. Now lie load I am going to consider as 3. Total factored load is going to become what? 10.875. Here also you can see 10.875. Now here bending moment along the shorter span, bending moment along the longer span. So here slight difference you can find. Along the shorter span 13.2855 and here 12.64. Due to what? Due to slight difference in the moment coefficient. But that we can consider. Okay. Now along the longer span it is 8 point, but in calculation it is 9. That is also very close to your manual calculation. Now if you are using the 8 mm diameter of bar, here the list of diameter of bars are present. You can change it with the drop down list. So I am going to choose 8 mm. 139 mm spacing is required. We are going to provide it as 100. Now 8 mm diameter as 205, but to match with our manual calculation I am going to take it as 175 along the longer span. Okay, so I am going to take 175. You can take 200 also because 205. So you can take 200 lower value, but I am going to take it as 175. This is your choice. So percentage of reinforcement along the shorter span, longer span, both are available. Provided depth is safe in flexure, means for the flexure requirement is 67, you have provided 105. Provided depth is safe in deflection also. Okay, in deflection actual is 40.286. In our calculation what we have calculated 40.28. Okay, in actual it is 40.28. Permissible is what? 47.18. Same is actually present here also. You can see 40 and about to 49. Slight difference is there. So your provided depth is safe in deflection also. Your provided reinforcement as well as overall depth of your slab is what? Safe for the shear also. Now check for the cracking. So cracking check is also passing the criteria, because what? We have provided the percentage of reinforcement in both of the direction as more than of 0.12%, plus spacing in both of the direction we have provided less than of 300. So if these two criteria is going to be satisfied, then you don't need to provide the check for the cracking. In cracking your design will be safe. This is your final design result. Slab as S2, you have to correct as S2, and overall depth is 130. 8 mm diameter of bar at a spacing of 100 along the shorter span. Along the longer span 8 mm die at a spacing of 175. It is a type of two-way slab. You just have to click over the send to schedule. Once you click over the send to schedule, this design result is going to be stored in your schedule list. Now suppose another type of the panel you are going to design as S3. Now you just have to click over the send to schedule. This sheet will automatically update the schedule S2 then S3, and once you click over this clear all the data from this list is going to be cleared. Hope that you all understood how to design smartly by using this Excel sheet. This Excel sheet is capable of designing one-way slab, two-way slab and cantilever type of the slab. All types of the slab you can design by using this Excel sheet. Welcome you all in ISO certified live training program ETABS, RCDC and Excel that makes you a professional structural engineer. In this training program you will learn everything about ETABS and RCDC from basic to advanced, real life project of medium rise structure from architecture plan to final design sheet, real life project of high rise structure with all advanced topics, design of structural elements using advanced Excel sheets. Have a look over the features of this training. Daily live classes conducted by expert for 1.5 hours. Recording of every session with lifetime access. Can interact with expert anytime 24/7. Exposure to real practice. ISO certification of training completion. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next. Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe, Excel and manual. In this training program you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second we will cover all the types of isolated foundation in CSI Safe software. In the third real life project we will cover the raft foundation, and in the fourth real life project there will be the coverage of pile and pile cap design of basement wall, and at the end of this training program you will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by expert. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next.